In this section, we're going to look at a method called partial fractions, which will allow us to basically tackle the integral of any rational function. Before we start, we'll just review a few things from algebra and pre-calculus. First of all, a polynomial. If a function p of x is a polynomial, it means it's a linear sum of powers of x. And here's two examples: x to the 5 minus x and 3x cubed plus 3x squared plus x plus 1. And the degree of the polynomial is the highest power occurring in the polynomial. So, for example, the degree of 3x cubed plus 3x squared plus x plus 1 is 3, because the highest power of x there is 3, and the degree of x to the 5 minus x is 5, because the highest power of x is 5. The fundamental theorem of algebra says that every polynomial can be factored into either linear factors of the form ax plus b, where a and b are real numbers, or irreducible quadratic factors of the form ax squared plus bx plus c, where a, b, and c are real, and b squared minus 4ac is less than 0. So, for example, 3x cubed plus 3x squared plus 1, if I pull out an x plus 1, I get x plus 1 times 3x squared plus 1, and x plus 1 is a linear factor with a equal to 1 and b equal to 1, and 3x squared plus 1 is an irreducible quadratic factor, because here a is 3, b is 0, c is 1, and b squared minus 4ac is minus 12, which is less than 0. X to the 5 minus x, I can pull out an x to get x times x to the 4 minus 1, and this x to the 4 minus 1 is a difference of two squares. It's x squared squared minus 1 squared, so I can factor that pretty easily into x squared minus 1 times x squared plus 1. And again, x squared minus 1 can be factored into x minus 1 times x plus 1, and the x squared plus 1 is irreducible. It cannot be factored using real numbers, real coefficients any further. The a is 1, the c is 1, and the b is 0, so b squared minus 4ac is minus 4, which is less than 0. A rational function is the quotient of two polynomials, px over qx. Now, if the degree of p is larger than the degree of q, I can write p of x as some polynomial multiple of qx plus a remainder where the degree of the remainder is less than q of x. And I can do this with long division. So, if the degree of p is greater than the degree of q, I can use long division to write this rational function as a polynomial plus a new rational function, which is the remainder polynomial divided by q of x. And the degree of that remainder is less than the degree of q of x. So if I wanted to integrate this function, this rational function, I would have to integrate a polynomial plus something called a proper rational function. A proper rational function is a rational function of the form r of x over q of x, where those are both polynomials, and the degree of r of x is less than the degree of q of x. Since every rational function is a polynomial plus one of these, and we already know how to integrate polynomials, we'll just concentrate on how to integrate these proper rational functions. We can write this rational function as a sum of what we call partial fractions. Every proper rational function can be written as a sum of partial fractions or mini-rational functions of the form a over ax plus b to the I, or ax plus b over a quadratic to the I, where capital A and capital B here are real numbers, constants, and I is a non-negative integer. All functions of this form we can integrate using our methods we've already studied. The integral might be difficult to calculate, but nevertheless it's possible to complete with the methods we've studied previously. Here are three examples. Suppose we ended up with three partial fractions of the form shown in A, B, and C. We could integrate using previous methods. A, we would just use the substitution u equals x minus 1, and the integral is a logarithm. For B, I could break this up into 2x over x squared plus 1 plus 1 over x squared plus 1, and the first one of those I can use the substitution u equals x squared plus 1 directly, and for the second one I can use tan inverse. For part C here, the integral of 1 over x squared plus 2x plus 3 squared, I could complete the square and then use the appropriate trigonometric substitution from the previous section. So we've reduced the integration of any rational function to being able to figure out what the associated partial fractions are, and then we can integrate all of these using previous methods. So that's basically the gist of what we're going to do in this section.